It is a pleasure to have Ken Yagi here with us today. Ken received his PhD at Kyoto University in 2012. Straight after that, he went to the University of Montana, where he basically was a postdoctoral fellow, and he made a name for himself by studying some universal relations for neutron stars that go by the name I love Q. So, this is a lesson, especially for the graduate students. If you want to make a name for yourself, find a catchy name for a paper. Then you become famous.
You reflected on that.
Huh?
It was good science also.
It was also very good. No. I'm saying that because that's exactly what I told Ken. But his point, is that marketing also matters. And soon after that, in 2015, he went to Princeton University, where he was a JSPS fellow, which is a prestigious Japanese postdoctoral fellowship, and he's currently faculty in physics at the University of Virginia. So Ken, apart from neutron star physics, he's also made a name for studying modified gravity, among other topics. But today he'll tell us about probing nuclear physics with gravitational waves via universal relations for neutron stars. Ken?
Thank you, Vasilis. Good afternoon, everyone. It's my first time visiting Tucson, and I'm enjoying this nice weather. So today I would like to explain a bit about how we can learn nuclear physics in terms of gravitational waves.
Which one is it? Maybe you push this in, Chris.
Okay. Oh, come on, it's not working anymore.
It's not working? So it's not
Sorry,
my fault.
It's not your fault. Sorry, Ken. It's okay.
You want the big lights offhand.
Oh, there you go. Now turn off the other. Now, yeah. It's okay.
It's okay.
I think it's fine.
Yeah.
Wait.
Yeah.
That's a little.
There you go. That's
It was something in her combination.
Thanks, Vasilis. Okay, so I would like to explain how we can learn about nuclear physics using gravitational waves, especially by using these universal relations. And I don't know your background, but LIGO found these gravitational waves, and if you have some object that's in motion, then they create ripples of space-time called gravitational waves. And this is an animation corresponding to the very first event that LIGO detected. Two black holes orbiting around each other, colliding, producing a big black hole, and then it settled down and no gravitational waves are emitted. And again, this was the very first event. Now they have found, is it working? Okay. Sorry, it's supposed to be animation. And so far they have found 10 binary black hole merger events, and this was the very first one, and Christmas Day event was this one, and now they have a bunch of others. But these were all for binary black holes, and today's focus is about neutron stars. What are neutron stars? If you have very massive star, then it undergoes a supernova explosion, and it forms some remnant, which is very compact object, and these are called neutron stars. For this animation, it produces what's called pulsar, where you have two jets emitted from this compact object, and if this light points to us, then we see a pulse. So this is called a pulsar, which acts as very accurate clock. To give you some basic facts, mass is comparable to the sun for a neutron star, but what's fascinating is that radius is only like 10 kilometers. So imagine that you take a sun and then compress the sun until it fits inside 10-kilometer radius. So you can imagine how compact these neutron stars are, and due to its compactness, the central density goes way beyond nuclear density. So that's why neutron stars are very interesting to probe nuclear physics, which is inaccessible from ground-based experiments. In August 17, 2017, let's see. This animation also doesn't work. Okay. Anyway, so there was an event, as you may know, that two neutron stars orbiting around each other and they're colliding. And in this case, they detected not only gravitational waves, but also all the other electromagnetic counterparts. So this marked dawn of multi-messenger astronomy. now we have not only photons, but we also have gravitational waves or gravitons that we can use to probe what's going on in our universe. And just by this single event, GW170817, we learned lots of physics, including astrophysics, like the origin of a short Gamma burst, or gravitational physics, like they managed to compare the arrival time of gravitons and photons to place bounds on the propagation speed of gravitational waves away from the speed of light, and this difference was constrained to 1 part in 10 to 15. And this ruled out many of modified theories of gravity that can explain current accelerating expansion of the universe. In terms of cosmology, they managed to measure the current Hubble constant, and this measurement has huge error bars. And this error bar, huge error bar, means that this new measurement with gravitational waves is still consistent with supernova explosion measurement and also CMB, which has a tension between the two, and the tension is more than 2 sigma. But today's focus is on nuclear physics. So let me go through what is the main issue about nuclear physics and how we can use neutron stars to probe nuclear physics. One of the largest uncertainties in nuclear physics is that we don't know what is the correct equation of state is in nature nuclear matter. Equation of state is the relation between pressure as a function of density, and there are many approximations or assumptions that people make to predict what should be this equation of state. But different assumptions give you different equation of state, and we don't know which one's correct. Probably none of them is correct. So we want to pin down what is the correct equation of state for nuclear matter, and the idea is to use neutron observations. And typically what people have done is to look at the relation between mass of a neutron star as a function of radius of a neutron star, which looks like this, which you can clearly see that this relation depends strongly on which equation of state you pick, which is great because if you can measure these two quantities independently, then you can plot a point in this plane with some error ellipse, and if this is your measurement, then you can say your measurement is inconsistent with stiff equation of state. And there is a nice paper by Fariel and Dimitrios and others who used neutron star X-ray observations to see how well we can measure radius of a neutron star. What they did is they took 12, I think, neutron star observations, and they derived probability distribution of radius for each neutron star that's shown in this left plot. And then they combined all these probability distribution to find the combined measurement of neutron star radius, which turned out to be 10 kilometers plus minus 0.5 kilometers. So this is one way to prove nuclear physics using neutron observations through like X-ray observation of radius measurement. But now we have new measurement from gravitational waves. So I'd like to explain first current status of probing nuclear physics using this new event that LIGO brought us. And I will move on and explain how universal relations that I'm going to explain can help us in probing nuclear physics, especially how you can apply these universal relations to these events. Then I would like to explain a bit about what we can learn in terms of post-merger signal via what's called coherent stacking that I did with Vasilis. So first I would go through the current status of LIGO's measurement, and the idea is as follows. Let's imagine that you have two neutron stars orbiting around each other. Then as these neutron stars come closer and closer together, the tidal field of one neutron star acts onto its companion, then this companion gets tidally deformed. This is a schematic picture showing two gravitational waveforms coming from two different binary systems. One has this tidal effect, so the red one corresponds to binary neutron star merger gravitational waves, while the black one corresponds to the waveform from binary black hole merger event. They have exactly the same binary parameters like masses and spins and so on. The only difference is whether you have this tidal effect or not. And you can clearly see the difference between these two waveforms, which means that gravitational waveforms encode information about this tidal effect. Now this tidal effect is controlled by the neutron star internal structure, which in turn is determined by nuclear matter equation state. So this means that if we can measure the amount of this tidal effect from gravitational wave observations, then we can map this information onto nuclear physics information. That's the idea. And the single parameter that controls the amount of tidal deformation is called tidal deformability, which is related to what people call tidal lab number, which is defined to be the ratio between the amount of quadrupolar deformation that you have on the neutron star due to the strength of the tidal field of its companion. So it's a linear response coefficient, and if this tidal deformability is large, then that means you can more easily deform an object. And this is a plot showing dimensionless tidal deformability as a function of neutron star mass for various equational state. And just like you can use mass radius relation to prove nuclear physics, you can use this relation to prove nuclear physics. Namely, if you can measure tidal deformability and mass of a neutron star independently, then you can say something about nuclear physics. This is the main idea. So the question is, what has LIGO measured? And since there are two neutron stars in a binary system, there is a tidal deformability associated to each of these neutron stars, but unfortunately it's very difficult to disentangle these two tidal deformabilities, and the reason is there is a strong correlation or strong degeneracy between these two individual tidal deformabilities. So what LIGO could measure instead is the dominant contribution of the tidal effect encoded in the leading tidal parameter, lambda tilde, that's given by a certain combination of two tidal deformabilities in a binary system, lambda 1 and lambda 2, and it also depends on the mass ratio of these two neutron stars. This is the probability distribution function, this dominant tidal parameter lambda tilde that LIGO and Vargo collaboration reported. If you pick 90% credible region, then basically LIGO say that this lambda tilde has to lie somewhere between 70 to 700. Great, so we have this measurement on lambda tilde, the leading tidal parameter. So now how can we map this information onto nuclear physics information? And what LIGO did is to pick, for example, one equation state and see how the lambda tilde should be with that equation state. And this is an example showing 7 representative equation states that LIGO-Vargo collaboration picked. And these black curves show probability distribution of how lambda tilde should be with each equation state. And some of these ones, especially the ones that predict large lambda tilde, has some widths, and that's because mass ratio has not been measured very precisely, so that's why there is some uncertainty in lambda tilde. And in terms of terminology, we say that equation state is soft if the slope of equation state is small, and those soft equation states tend to produce more compact neutron star with smaller maximum mass. Probably it's easier if I show the mass radius relation and show the correspondence between each equation state and mass radius relation. Softer equation state, this class tends to produce more compact or smaller radii neutron stars, and they tend to have smaller maximum mass. On the other hand, stiffer equation state tends to produce larger radii neutron stars with larger maximum mass neutron stars. And softer equation states tend to produce smaller tidal deformability, while stiffer equation states tend to produce larger tidal deformability, because stiffer ones tend to produce fluffier and less compact neutron stars that are easier to deform. So that's why they have a larger tidal deformability. And what this LIGO's measurement is telling you is that LIGO's data preferred softer equation states. And this is actually consistent with what Ferrier and Dimitrios found from X-ray neutron star observations, that radius has to be somewhere around 10 kilometers, which is a small radii, so softer equation states are more consistent. LIGO people went one step further and they tried to map this measurement of lambda tilde to actual equation state plane constraints. What they did is they took what's called spectral equation state, which has something like 4 generic parameters. So they did not use any specific equation states that predicted by nuclear physics, but rather they picked some phenomenological equation state that has certain generic parameters that can construct various equation state. And from their tidal deformability measurement, they placed bounds on each of these each of these generic EoS parameters. And then they figured out what is the allowed region should be in this equation state plane. And this blue shaded region is the bound that LIGO and Virgo came up with. But this spectral equation state assumes that equation state is nice and smooth. So what this does not capture is a possibility of having first order phase. Yes.
Sorry, can you go backwards for a second?
Yes.
So
Yes.
what are you defining as rho nuclear?
This is
Density
the
of
nuclear
what?
saturation density. It's basically nuclear density. Nuclear
So
density means
for a specific nucleus? Or
no. So nuclear density means that even if you add, let's say, one atom,
Yeah.
the density doesn't change. Essentially, that defines basically nuclear density.
It's about 2 times 10 to the 14 grams per cubic centimeter.
Okay, any other question? Okay, so what LIGO's spectral EoS does not capture is this possibility of having first order phase transition where in the low density regime you may have nuclear matter, and then as you increase your density of pressure, it transitions to quark matter. And depending on the surface tension of nuclear matter phase and quark matter phase, you can have continuous or discontinuous transition. But this kind of phase transition equation state does not, it's not captured in the LIGO bound. So Vasilis and I and other collaborators asked ourselves, is there a possibility that these kind of equation states are still consistent with LIGO's measurement or not? And some interesting feature happens if you have this kind of equation state. If you look at mass radius relation, for example, with this red equation state, then mass radius looks something like this, which has funny behavior. Usually mass radius relation looks like this red one. And if you have this kind of orange mass radius relation, then what you can have is that for a fixed mass, you can have at least 2 different stable configurations of compact stars. The first configuration, which has larger radii, corresponds to actual neutron star, where this star is made up of nuclear matter. As you increase the central density, then this moves on to this new branch where it's called hybrid star, where core region is made up of quark matter, and in the envelope region it's made up of nuclear matter. And it has more smaller radii, so its hybrid stars are more compact than neutron stars. And people call these twin stars because for fixed mass you can have 2 different configurations. So what we did is we tried to compare these predictions against LIGO's measurement. This is plotting lambda 1, which is the tidal deformability of the primary neutron star in the binary neutron star merger event. Primary means that this neutron star has larger mass than the companion. Lambda 2 on the vertical axis is the tidal deformability of the secondary neutron star, which has smaller mass. If you have equal mass system, then lambda 1 has to be equal to lambda 2, so the relation should follow this dotted line. Since we are assuming that M1, the primary mass, is larger than the secondary mass, this lambda 1 has to be equal to or smaller than this lambda 2, so all we care about the region which is above this dotted line. Okay. Now, as I said, it's very difficult for gravitational wave observations to disentangle these two, and what LIGO could measure is only the leading tidal parameter. But since that leading parameter is constructed from this lambda 1 and lambda 2, you can map bounds of lambda tilde to bounds on lambda 1 and lambda 2 plane, which is shown by this blue shaded region, 50% credible limit and 90% credible limit. So basically, anything inside this blue shaded region is consistent with LIGO's measurement. Now, if you pick one equation state, then you can predict what the relation should be between lambda 1 and lambda 2. For example, if you pick this orange equation state is your correct equation state, then lambda 1, lambda 2 relation should look like this orange solid curve and also this orange dotted dashed line. Why are there two different branches? Because if you start from equal mass system and then you decrease mass ratio, you climb up this orange solid curve, and you have as a binary two neutron stars as your constituents. So you have two neutron stars in the same branch in this part of the lambda 1, lambda 2 plane. And this is still consistent with LIGO's measurement. Now, as you keep decreasing mass ratio, meaning that you make the larger mass even larger and smaller mass even smaller, then eventually this larger mass neutron star goes onto the new branch, the hybrid star branch, and now you can realize a binary system with one hybrid star and one neutron star. And now you shift in this plane to this dotted dashed branch. And you can see that this one is even more consistent with LIGO's measurement. And the reason is because now you're cutting into this 50% credible region. As I said, LIGO's measurement prefers softer equation state, and if you add more matter or additional degrees of freedom, like bulk degrees of freedom or hyper degrees of freedom, then you tend to make your equation state softer. So you are making your equation state more and more consistent with LIGO's measurement. So the bottom line here is that LIGO's measurement of this event could be a merger of one hybrid star and one neutron star colliding. Yes.
What is the Q for the lowest point on the dash curve?
Lowest point on the, you mean here?
Yeah, like when do you jump there? At what Q?
That's a good question.
If you don't remember, that's fine. I'll look in the paper.
Yes, I'm not sure if we say that in the
No,
paper.
we don't.
Oh, okay.
Well, because it's different equations of state. It's not just one equation of state. So,
Right,
but it's not.
yeah.
It's not very different from, I don't know, 1.1 or 1.2. It's because the transition occurs fairly low. If you can see on the plot
Right.
there.
So transition occurs at 1.5, and then equal mass corresponds to 1.36.
Right.
So,
Yeah, just curious, how low do you need to make the second star mass?
something like 1.2 solar mass,
1.2? Okay.
something like that.
Thank you.
Any other question? Okay. Next, let me explain what universal relations are and how you can use those universal relations to probe nuclear physics using gravitational waves. So universal relations mean that unlike mass radius relation, which depends strongly on which equation state you pick, some relations in neutron star observables don't depend strongly on underlying equation state. And one example is this I love Q relations. So what we did is we looked at moment of inertia of a neutron star I and quadrupole moment Q. This tells you the amount of quadrupolar deformation due to spin of a neutron star, and also tidal deformability or tidal love number. And we constructed a bunch of neutron star solutions, picking different equation state, and we looked at relations among these quantities. And what we found is that no matter which equation state you pick, which are shown by these different markers, basically you just get a single curve. One relation with one equation state lies on top of each other, so that's why we call these relations universal. The single parameter along this curve is mass. As you increase your mass, then you move from right to left, and you're approaching the black hole limit. These universal relations are not exact. There is small amount of equation state variation hidden, but the amount of equation state variation is something of order 1%. So these universality are pretty tight. There are other I see. One thing to mention is that we also checked that these universal relations holds for hybrid stars. We found another types of universal relations, and that has things to do with tidal deformabilities entering in the binary system. As I said, it's very difficult to disentangle two tidal deformabilities in a binary system, but what we did is we looked at the relation between symmetric and anti-symmetric combination of tidal deformabilities in the binary system. Symmetric combination just means you're taking the average of two tidal deformabilities. Anti-symmetric combination simply means you're taking the difference between these two tidal deformabilities. And in this case, the relation looks like these. Again, different colors corresponds to different equation state. And the relation here also depends on mass ratio Q, because now you have two neutron stars into play, whereas in the previous I-love relation is purely about a single neutron star. So you need to specify what mass ratio you want to consider, but once you specify your mass ratio, then you do find universality. This time universality holds to something like order 10%, so it's not as universal as the previous I-love correlations, but still these could be useful in gravitational wave observations. And what LIGO and Vorko collaboration did is to use actually these universal relations and see how much improvement we gain in terms of bounding lambda 1 and lambda 2. Again, this is the plot that the same plane, lambda 1 as a function of lambda 2. If you specify one equation state, then you can predict what the relation should be. Here I picked 7 representative equation state. If you don't use any universal relations, then the 90% upper bound on this plane becomes something like this black solid curve. On the other hand, if you use universal relations, then what you can do is you can reduce the amount of correlation in your gravitational wave data analysis. Since you have two tidal deformabilities in play, you need to include at least two tidal parameters in your data analysis. What LIGO did is LIGO included lambda tilde, the dominant parameter, but they also introduced another subdominant tidal parameter, what they call delta lambda tilde, and then they did some data analysis. But instead, what you can do is, since we have universal relations, we only need to include one tidal parameter, and no matter what the correct equation state is, you can automatically get the other one. So you can analytically break the degeneracy between these two tidal parameters, and you do gain, you have better accuracy in measuring tidal effects. So if you use universal relations, then the 90% credible upper bound on this plane looks like this blue curve. And the density of these dots show the probability distribution in this lambda 1, lambda 2 plane if you use universal relations. So basically, if you use universal relations, you can break some degeneracies between tidal parameters, and you can shrink the allowed region from black line to blue line. So you have better measurement of tidal effect. And there's another nice universal relation found by Caroline and Ariel and Dimitrios. And in case you didn't remember, this is the relation. This shows lambda tilde, the dominant tidal parameter, as a function of radius of the larger mass neutron star, and they picked different equilibrium states and different masses for the primary neutron star. But you can see this nice universal behavior between these two quantities. And this black line is, at first thought this is a fit, but I found out that it's not. And they actually did some nice analytical calculation, and they predicted analytically what the relation should be, which lies beautifully with these numerical data points. So by using this new universal relation, what you can do is you take lambda tilde measurement from LIGO, and then you can map this lambda tilde measurement to bounds on radius. For example, if you have the upper bound on lambda tilde to be 800, then you can say that radius of the primary neutron star has to be smaller than 13 kilometers. again, which is consistent with the X-ray observational result. So far, I have explained how you can use universal relations to infer nuclear physics information from gravitational wave observations, but you can actually go in the opposite direction. If you like, you can take LIGO's measurement and you can try to improve universality in these relations. And to address this question of how much improvement you can obtain by using LIGO's measurement in terms of universality, what we did is we constructed two different classes of equilibrium state. One is called unconstrained equilibrium state, where we don't care about LIGO's measurement, we just construct equilibrium state randomly. On the other hand, we constructed constrained equilibrium state, where we restrict ourselves to equilibrium state that are consistent with LIGO's posterior in this equilibrium state plane. It's a bit difficult to see, but there is a blue shaded region behind all these curves, and that shows the LIGO's 90% posterior in this equilibrium state plane. And we looked at, for example, the universal relation between antisymmetric and symmetric combination of tidal deformabilities. The upper panel is the same essentially as what I've shown you already. The bottom panel shows the amount of equilibrium state variation hidden in these universal relations. The brown one corresponds to unconstrained equilibrium states that we originally used, and the green one are the new equilibrium states where we restrict ourselves to be the ones that are consistent with LIGO's measurement. Typically, the unconstrained ones predict EOS variation to be something like 20%, whereas if you just restrict ourselves to the constrained class, then equilibrium state variation reduces to something like 7%. So basically, by restricting or by imposing LIGO's bound on equilibrium state, we can improve the universality in these relations by a factor of 3. And this could be important in future measurement, as I'm going to explain now. Right now, LIGO has measured lambda tilde to with some accuracy, and that purely comes from statistical error due to the detector noise. If you want to use these kind of universal relations, then of course we have to worry about the amount of equilibrium state variation, because these universal relations are not exact, and these equilibrium state variation produces systematic errors. So we need to compare the amount of statistical errors and systematic errors, and as the detector sensitivity improves, statistical error will decrease. So maybe at some point in future, systematic error starts to dominate. So the question we wanted to address is, do we really need to care about these equilibrium state variation? In other words, at what point in future the systematic errors induced by equilibrium state variation in this universal relation becomes dominant contribution compared to statistical errors? So to address this question, we did some data analysis to see how well we should be able to measure the tidal effect with future detectors. Right now we have finished advanced LIGO 02 round. The sensitivity as a function of frequency looks like this flat curve. They have detected one event. In future, they are trying to have its design sensitivity, and with the most optimistic case, they may find 300 binary neutron star merge event. Moving on, they will upgrade into A+, which has been funded recently by NSF. And furthermore, they will move on to Voyager detector, which may find 30,000 binary neutron stars. At this point, if you want to go beyond, they have to go somewhere else, not just the LIGO site. And one proposal is called Cosmic Explorer. Somewhere maybe in Utah, they are trying to build large ground-based gravitational wave detectors, which has arm lengths 10 times longer than LIGO, 40 kilometers. And they will, if they can realize this kind of detector, then sensitivity improves a lot. Especially, they have more sensitivity in this low frequency part. And there's another proposal in Europe called Einstein Telescope. they are trying to build this detector underground, and they make cryogenical cool to reduce the amount of thermal noise. And they have even more sensitivity in the low frequency regime. And again, in the most optimistic scenario, they may be able to find millions of binary neutrons emerging. What we did is we take these detectors, we run Fisher analysis to see how well we should be able to constrain or measure tidal effect. Those are statistical errors, and then we are going to compare those statistical errors against systematic errors due to universal relations. I'm going to show you a plot showing the the measurement accuracy of tidal deformability at neutron star mass of 1.4 solar mass as a function of signal to noise ratio for the GW17 or 817 like events. For example, O2 has found this event with SNR of 32, so it corresponds to this part here. Advanced LIGO should see this event with SNR of 90, so Advanced LIGO comes here, and A+, Voyager, Einstein Telescope, and Cosmic Explorer, and so on. As you increase your detector sensitivity, your signal to noise ratio keeps improving. And this blue shaded region is a prediction of how statistical error should decrease as you increase the sensitivity of these detectors. The reason why it has this band is because we don't know the merger rate. The merger rate that I was shown in the previous slides are the most optimistic case, but it has a huge uncertainty. And we try to combine multiple events, but depending on how many events they will see, we have different predictions for this tidal deformability measurement. So that's why there is this blue band uncertainty. On the other hand, systematic error coming from those universal relations have something like 10 or 20. So right now, statistical error dominates over systematic error, but as detector sensitivity improves, especially in the Voyager era, which may happen in 10 years from now, these systematic errors start to dominate over statistical errors. So if we still want to use these universal relations, then we need to make sure that we keep upgrading these universal relations by previous measurements. Okay. Moving on, there is yet another universal relation that could be useful in terms of mapping LIGO's measurement into nuclear physics information, and that has things to do with constraining nuclear parameters. Spectral equation state that LIGO uses is one way of parameterizing equation state, but there are other ways to generically parameterize equation state. And what nuclear physicists usually do is to take equation state and Taylor expand about nuclear saturation density and also symmetric matter. What I mean is as follows. For example, if you take energy per nucleon, which depends on the total number density and also this parameter delta that tells you the difference between neutron number density and proton number density, then first you can try to expand this quantity about symmetric matter, meaning delta equals 0. So you have the leading to be the symmetric energy per nucleon, and you have some correction due to having asymmetry in your nucleon. And if you further take, for example, this asymmetric part, then you can further try to expand this about nuclear density. So you have all these Taylor expanded coefficients, J naught, L naught, and K sim naught. These Taylor expanded coefficients are what people call nuclear parameters, and they control equation state around nuclear saturation density. Let's see, and for example, if you pick this second order Taylor expanded coefficients, which are called curvature of symmetry energy, then it turns out that there is a strong correlation between this nuclear parameter and also lambda tilde, the leading tidal parameter that LIGO measured. Each point here corresponds to one single equation state. If you pick one equation state, then basically you can plot a point in this plane. Different colors corresponds to different classes of equation state. in previous work by Malik and others, they only considered green and blue ones. Those are relativistic mean field and also SCARM type equation state. While we phenomenologically constructed equation state wider range, and the new ones are shown in red. But even if we add those new equation state, you can still have this nice correlation. On the other hand, the LIGO measurement are shown by this blue shaded region. So what you can do is you can take LIGO's measurement on lambda tilde and try to map this information onto nuclear physics information by using this correlation. To do that, what we did is this is the same plot as the previous one. You can see all the orange dots that corresponds to each different dots in the previous slide. Based on this scatter, we constructed a two-dimensional Gaussian probability distribution on these two parameters. Now, since we have LIGO's probability distribution on the horizontal axis, we can combine these two different probability distributions, marginalize over lambda tilde to get a single probability distribution on nuclear physics parameter, the curvature of the symmetric energy. And this is the probability distribution. These higher order nuclear parameters are very difficult to measure using nuclear experiments on ground because nuclear experiments are more sensitive to what's going on in, around nuclear saturation density, whereas neutron star density larger than nuclear saturation density, so they are more correlated with higher order parameters. Okay, yes?
Why does the structure in the posterior for lambda tilde disappear here?
It's basically because this two-dimensional probability distribution is Gaussian, and yeah, so this Gaussian is determining this probability distribution. Yeah, at first when my grad student wrote this, I didn't believe it because I thought you would find more funny behavior due to this, but yeah, he was right. Yeah. Okay. So now, for the remaining of my talk, I would move on to the post-merger phase. So far, I've been focusing on what happens in the late inspire part of the waveform, but there are also rich information encoded in the post-merger part of the waveform. So this part is the inspiral part, and after the merger, what typically forms is a hypermassive neutron star or supermassive neutron star that's in oscillation, producing this kind of waveform. And if you look at the gravitational wave spectrum, gravitational wave amplitude as a function of frequency for various equational states, then typically what you find is that there is some peak, but this frequency of this peak depends on which equational state you pick. In other words, if you can measure this spectrum in the post-merger phase, then by measuring, for example, this frequency of the peak, you can say something about nuclear physics, nuclear matter equation state. But the problem is that this black curve here corresponds to advanced LIGO's design sensitivity noise curve, and you can see that as frequency is increased, the sensitivity becomes worse and worse. The problem is that this peak frequency happens to high frequency for the LIGO detector, so that's why it's very difficult to detect this post-merger signal. And for example, with GW17 ON17, LIGO did not detect this post-merger signal. So what we tried with Vasilis and Fuanyan and others is to somehow stack multiple events and then try to enhance signal-to-noise ratio. And the key here when stacking is called coherent stacking. Let's see. So basically what you need to do is to first you need to somehow align the phase of each signal coming from different sources. And once you align the phase, you can stack events together. For example, if you don't do this phase alignment, then this is what you find. The post-merger signal has different phase depending on what mass you have as a remnant neutron star. And if you don't align your phase and just add them together as they are, then there will be a phase cancellation and you cannot maximize the amount of information available. On the other hand, if you can somehow align the phase, then now each signal is in phase, and you can, if you add them together, you get a maximum enhancement. But to do this kind of alignment, well, it sounds like you need to know what is the correct equation state a priori, because the amount of this phase is controlled by the true equation state. So unless you know what the equation state is, it sounds very difficult to align this phase. But there is again nice universal relation that you can use to align this phase. The trick is as follows. This plot shows the peak frequency over the mass of the remnant neutron star as a function of radius of a neutron star at 1.6 solar mass for various mass of the remnant neutron star. What this is saying is that there is nice correlation between these two parameters. So basically this is saying that peak frequency is linearly proportional to mass, and there is some coefficient that depends on this radius at 1.6 solar mass, which encodes all the information about nuclear physics. But if our goal is to just align the phase, then we don't care what the parameter is in this part. All we need to know is that peak frequency is linearly proportional to the mass of the remnant neutron star. This means that once we have information about remnant neutron star of different events, then we can rescale our peak frequency according to this prediction that the behavior is linear. Then we can align the phase to some targeted frequency. Then you can stack things together. So what we did was we did some Monte Carlo simulations to see how much improvement in detection probability we gain by stacking coherently multiple signals. This is the probability distribution as a function of signal-to-noise ratio threshold. If you assume Cosmic Explorer is online, if you do 1 year measurement, and if you don't do any stacking, you just have a single event. Then, for example, if you set your SNR threshold to be 5, the detection probability is something like 35%. So the chance is not that small, but you can increase this detection chance by coherently stacking multiple events. If you do that, then the chance of finding this kind of post-merger signal enhances significantly to something like almost 100%. So this, in this paper, we basically formulated how to coherently stack signal and how much enhancement we gain in terms of detection probability of post-merger signal. And once we can detect this kind of post-merger signal, then we can place very stringent bounds on the radius of a neutron star. But the problem is, since we are using this universal relation between peak frequency and radius of a neutron star, again there is systematic error that come into play, and actually this systematic error dominates over statistical error. But still, the prediction is that once you can measure this post-merger signal, then you can predict the radius of a neutron star to something like 200 meters. If your neutron star radius is, say, 12 kilometers, then this measurement accuracy is less than 2% error. Okay, so to conclude, the take-home message is that universal relations do help in improving the tidal measurement, and also there is nice correlation between nuclear physics parameters and what LIGO measured as the leading tidal parameter, which you can use to map LIGO's measurement to nuclear physics information. On the other hand, you can go the opposite direction. You can use LIGO's measurement to further enhance the universality of these relations. And finally, if you can measure this post-merger signal, then that's huge. And to do that, one way is to coherently stack these signals. Okay, that's all I wanted to say today. Thank you very much.
Right, we have time for
universality works, which is secretly what I want to understand. You know, you want to know why. So why are these universal relations? What have we learned about gravity?
We propose this idea of having some kind of symmetry emerging as you increase compactness. If you look at how isodensity contours inside a star behaves, then if you have fluffy stars like white dwarfs or brown dwarfs, then what you find is that in the surface you have this elliptical shape, and as you go to the core region, you have more like a sphere. So there's a variation in the amount of ellipticity that you have inside a star. On the other hand, if you do the same for neutron star, then you see almost you see less variation in this amount of ellipticity inside a star. And what we did is we showed that this amount of variation inside a star in terms of ellipticity plays important role in the amount of universality, and this symmetry becomes exact if you have constant density star. So there's an argument saying that equilibrium states for realistic neutron stars are in some sense very close to constant density equilibrium state in terms of these universal relations. But we just provided some evidence, and we don't have any mathematical.
Is GR important? I mean,
it is. If you choose some theory that's different from GR, then you get some different relation.
but it's still a universal.
Yes, it is true universal.
And it's true in Newtonian limit. So it doesn't have much to do with gravity.
Right.
But do you get a universal relation in any theory of gravity?
Well, as far as people have seen,
okay.
I think yes. I don't remember any example where if you look at theory other than GR, then you break universality. That I don't recall. But that doesn't mean that.
Does Chern-Simons not break it?
No.
No?
Dynamical Chern-Simons, but it's different than the GR.
Yeah, it's different, but still you do find EoS universality.
If the scale of your theory is 10 kilometers, it will break. As you go above and below the scale, right, you will have a break between the two of them, so it will be non-universal in that sense.
Any other questions?
I was curious about the upper right plot there. Your underlying parameterization of the symmetry energy have three parameters, out of which one is irrelevant, constant, and the other two determine effectively the typical pressure and then the effective polytropic index of your equation of state. So I would have expected that, I mean, the reason probably that you get this spread is because the other parameter varies along that direction. Why not convert lambda tilde to a two-dimensional correlated constraint between the two parameters of your symmetry energy?
What do you mean exactly?
So you have two parameters that matter, right? Whatever K and L, right? So I bet what changes for a given lambda tilde, the reason that you have a spread is because L is different along the vertical direction.
Right.
So instead of converting it only on marginalized one, you can take lambda tilde and convert it into a correlated constraint in K and L.
I see. Yeah, I think you can do that. Yeah.
Because a lot of the, I mean, the reason that the blue points there, which is a particular equation of state for a line, is most nuclear physics calculation actually have anti-correlation between K and L, and that's why you get a single line there. And it would be interesting to see whether the correlation or anti-correlation that you get from LIGO, I mean, even though it might match nuclear physics, it might be offset in the two-dimensional plane. So I think you're actually going to get much better results than just marginalizing it only one.
And by better, you mean that you can place bounds on K-sim and also
like constrained bounds on the two, then that will be offset from what different equations of state will. So even though marginalizing them, they overlap.
But what we did is, if you take this K-sim and another parameter, let's say L0, then we can create a linear combination of these two to make this correlation even stronger.
Correct.
But then the problem is this L0 introduces additional error because this has error from nuclear experiments, and the bounds on K-sim becomes actually worse.
Correct. But if you do it separately and compare to the correlated errors from nuclear experiments, I think you'll find them offset most of the time. Maybe. Yes.
interesting.
Any other questions?
I have a question about the plot down.
We're going around.
Well, I had it during the talk, but I kept it actually. I saved it for the end. So, so is there some kind of sense that you may actually converge? Because it seems like you have your theoretical calculations, giving you LIGO a way to constrain the equation of state better. Now you get the information from LIGO. You try to find a better universality relation. You can go back and you can iterate. Is there some? Did you look at whether you could actually have some kind of mock?
Well,
data that could show some kind of convergence to within the statistical errors or something like that?
if you want to use LIGO's data to improve universality, then you cannot use this improved universal relation to measure tidal effect, because then you can only do one part. Because
well,
you only have one single set of data.
Oh, but I'm saying you start with a set of data right now. You improve it. Now in the future you will get.
In future,
yeah,
yes,
you will
that's
have
right,
new
that's right.
observations.
Yes.
So can you see whether you could actually do something, or you could just or is it the idea that you would use this larger set of data to place a better constraint on the universal relations? I'm just curious as to.
Actually, the point here is that you should use future events to keep improving this
The universality. Okay.
But we haven't worked out how much improvement we gain, because there we need to make some assumption of how much we will be able to shrink the bound in the EoS plane as the detector sensitivity improves. That we have.
And is the universality improved by focusing on the 90% confidence intervals on lambda, or if you
no, for this one we used the bound on the EoS plane obtained from LIGO, P as a function of the plane. There.
but that's also within essentially, which is also 90%.
Till the,
Okay.
Yeah.
Any other questions?
Just for asking every picture up there. Maybe this is obvious, but the bottom right picture, how are you getting the same curve from 3 different masses? I would think everything would scale differently in time.
So we, at first, they have a different phase,
Yeah.
but we align the phase.
So you shifted them left and right? Okay.
Exactly, that's right.
Okay. That's also unexpected to me. But
It also rescales with the mass.
That's right.
The mass
Yeah,
is the
that's
main
right.
thing that governs the time scale.
yeah, right.
So, did you have a question?
Yeah, I was going to ask a little bit more about using using the data that we already have to rule out equations of state. If we do have a situation where a hybrid equation of state creates twin stars, and the one event that we observed is in one part of, like, the two were in had a particular Q that limited you to one part of the space. Is there a danger that you've thrown away parts of the universal relations that you should have kept?
There is. These are only valid for non-hybrid stars. If I include hybrid stars, then the universality breaks down.
Okay. I hope nature is kinder to us than that.
But it's more interesting if you have.
Sure, yeah. It'll keep us employed longer.
I'm sure there's plenty of problems to keep us employed. Okay, there are no more questions. Let's thank Kent again.